everyone. In today's video, I will show you how we can map vulnerability to. Actually, it's possible to map for different hazards, but different parameters can be used to calculate a hazard vulnerability index. So in this particular map, I will show you how we can map vulnerability to landslide. Landslide is actually becoming more common in high altitude and with the areas having high topography. And it is common in many parts of Ethiopia during summer season particularly. So to map this, actually we need to select a particular region. For example, in my case, I'm interested to Sidama region because I heard and I saw like last few years there are many landslide events taking place. Of course, it's common in like the southern and central part of Ethiopia. So landslide is one of actually prominent hazard in Ethiopia. So to do that, we need to load an SF package here and deploy a package to modify our data, to rearrange our data, Terra package to read different raster data types like rainfall, graded rainfall, and graded temperature, and whatever rain data. So here we read Ethiopia shapefile, and from that we subset and we filter and take only Sidama region. After that, we transform its projection to the projection of our interest. In our case, we are interested for this particular projection. And then after doing that, we read rainfall data. And after having rainfall, actually I downloaded this rainfall data from Terra Climate dataset, which is freely available. You can download for your analysis, and that is 4-kilometer data with 4-kilometer resolution, and which is I think the highest resolution available data set. It has, of course, as many graded data set, it has its own limitations, but it is I found it is sufficient and it's okay for many parts of the globe. So then we need to call this library to get elevation data. So we get elevation data using this function, which comes with this package, and then we give the location we are interested, because we are interested in Sidama region, which is assigned to shape here. Then the zoom level we decide, and the location that we're interested. Then after downloading and having all this data, we crop our data to the interest region. In our case, we are interested for Sidama region only. I can do this for a whole country, but on my machine that is a little bit having like high resolution data, it requires a lot of space, and my personal computer takes a long time to process. That's why I'm interested to plot only this particular region. Then I mask that data to Sidama region again. Then I take time. It is from like I downloaded rainfall from 1981 to 2015, and then I calculate annual average for that particular area. Then from the annual mean, I change the projection to the same as that of the elevation model. Then I have to change also the resolution to the higher possible available resolution. And then after having the same resolution for both of these data, they looks the same by now. And then I extract slope from the elevation model using this function in degree. Then I plot actually the slope, and it's plotted, and it looks like this one normally here. This is only elevation, and elevation looks like this one. Then elevation can be reclassified into a matrix. So depending on elevation, for example, depending on the slope, we can classify if the slope is like a lower slope, there is low vulnerability to the landslide. High slope areas are more susceptible to vulnerability than the low slope areas. Low slope like flatlands are not really susceptible to landslides like that of the high altitude areas. So therefore, high slope areas. Here, if we have like slope 5 to 15, that is, not that, again, not that vulnerable. And if it is between 15 and 30 is moderately vulnerable, and if it is 30, between 30 and 90, that is highly vulnerable. We develop these uh, uh, classes. So for your actually interest, you can change this according to the literature and according to many other things. You can determine that. Then based on the rainfall, for example, how much maybe rainfall going to cause a landslide. Most in our case, like mostly landslide is associated with rainfall and that of the saturation point of the land water holding. So if there is highest rainfall and the area is highly vulnerable to landslide than the lower areas, low rainfall receiving areas. So we decide also like the cluster of like low vulnerability, medium vulnerability, and highly vulnerable depending on the amount of, again, rainfall. So I cluster as like less than 800 milliliter rainfall, that is annual average rainfall, that is not really like less vulnerable. And between this and this is moderately somehow slightly vulnerable. This is moderately vulnerable, and this is like the areas receiving more than 1,600 or 2,000, or in case 3,000 millimeter rainfall, that areas, and maybe higher, that areas could be more vulnerable than the other areas. So we run this one. So based on, of course, like many literature, you can read literature if you're interested to determine a landslide vulnerability. Landslide vulnerability is not only, dependent on these two variables. You can consider many variables, and you can rate the vulnerability. Which factor causes like high vulnerabilities than the other factor as a determinant. So in our case, I rate slope as contributing more than that of rainfall. Rainfall contributes, of course, less than that of the slope. Slope is like, if it is a hilly slope, is more susceptible to landslide than the lowlands and the flat areas. So then we generated now like the landslide index, so landslide vulnerability index. Then we can plot that landslide vulnerability index, and it looks like this. Look, these areas, for example, this is not a good color. We change this color later, sorry. But for now, like we can see these areas, for example, these areas, and areas over here are more vulnerable than the other areas like here. And here, of course, I know these areas are lowlands and these areas have like high slopes. So it looks like, I mean, more realistic. So we go further to plotting, like using GG a plot, which is which creates like very appealing maps. So we go for that. We change our data frame, our data into data frame, and we assign variables, like we change the name of variable x, y, and as I said, variable as vulnerability. We can see like the head of this data. So x is like here longitude and y is latitude, and a vulnerability, the third component is here. So we assign first that, like which one is low and high, and so on, and also color for the very low ones looks a little bit whitish, and low ones looks a little bit like green, and not really green, moderate, a little bit yellowish, and the orange one is high vulnerable, and very high vulnerable is more afraid. So now we are creating a plot. We call like our data here, this vulnerability data frame is created. So we call gg function, and we are plotting raster. Then we call the data that we created here, and x and y are there, y and y, x and x we assign for x, and y is assigned for y, because y is already there in our data set. We give the same value. Otherwise, if we assign that data, I mean that value name as latitude and longitude, for example here longitude, if we assigned, but now we keep x as x and y also the same, and then classes has to be filled for the data, and other part of this gg plot remains the same. I added only like geo data here as on the top of as overlay Sidama region geom. So otherwise, the other thing remains the same here. I have shown you actually in another ggplot how it works. Like the basics are here, actually, like up to the color. This part is the basics. The other part is only to beautify, to add some, I mean, spices on our plot, and to make it appear very nice looking. We're going to add the other parts. So now I run this command to have a plot. Now the command is run already. I put like assigned a as a val plot, then val plot going to appear by now, right now here. Then how to save that plot as for later use is here. Once you create this function, you only change maybe this part and this part. This part is like the name of plot that we produced here, and this is the name that we want to save our file in the working directory. This is width and height of the plot. Then this is resolution of the plot. This is in the quality of publishable plot. Okay, so we can save clicking only this function. you can see how this plot looks like. I used here like rainfall, elevation, and slope. Actually, elevation is actually slope is derived from elevation. So as you can see, this area and some pocket areas over here and over these areas, it looks like highly vulnerable. Of course, for my knowledge, these areas are really vulnerable, and we had for the past few years too many landslides. Uh, Perhaps in every year, it won't be in the extent to damage a lot of infrastructure and displace many people, but at least one family or two family going to displace it in or killed by this particular hazard. And this is the landslide vulnerability map for Sidama region. And this can be done for Ethiopia as well, but a little bit it requires space, and it requires like a little bit more time. So that is it for today, and don't forget to like, subscribe, and share my channel. If you are interested to produce such plots for your area of interest or for your research, I will put the link of this particular code under this actual video, and you can go to the GitHub and you can find free of this code, and you can produce your own plots like this. Thank you very much.